Thank you, David. That's a tip. So let me just, this is a kind of a look at quasi-linear theory, primarily for the Vlasov-Poisson system, which is not one familiar, I think, to most of you. And I think most of this won't even be familiar to the plasma physicists. It's a kind of a specialized industry within plasma physics, but it's a fundamental problem. And you might ask, why am I doing this? And it's because there's been a lot of discussion of quasi-linear theory in this program, and particularly in the last workshop. And let's just say it raised my blood pressure a little bit, as you might have gathered. And particularly the statements about, the field was to a large extent developed in plasma physics, not completely, but to a large extent. So I thought it'd be nice to kind of have equal time, as they say in political debates. And from here on out, QLT refers to quasi-linear theory and not quarter pounder with lettuce and tomato. That's for David's as a fan. So these are my recent and past collaborators and all, and I don't have pretty pictures of everybody. And while for this, let me mention a series of workshops on the Vlasov-Poisson system that were run by Uriel Frisch about 8 years ago that were very interesting and re-sparked my interest in this. This is a subject I've worked on and off for a long time, but haven't been thinking about recently until things raised my blood pressure. So a little bit of philosophy. By the way, we'll come to it. In the oft-used comment of George Box, the statistician, all models are wrong and some models are useful. Quasi-linear theory is a useful model, okay? The second point, I'm here neither to praise it nor to bury it. And as I said, I hope the zealots of either sign go away unhappy. And the third message is this stuff, I think, often is dismissed, particularly by students before exams in plasma physics, as trivial. It's not. It just looks that way. So it brings to mind an old Haitian proverb I read about once. If you're not confused as we go along, you don't know what's happening. It's a good thing to keep in mind, I think. You can skip that. So this talk tells a story of sorts, and it starts with a heavy dose of the basics, and then we'll talk about nonlinear wave-particle interaction, and some of you will see some familiar ideas from other realms along the way here, and then we'll come to the challenges to quasi-linear theory, particularly what are called phase space granulations, and just think of those as eddies in the Vlasov fluid, and their implications for enhanced growth. And in particular, a theory by Adam, Laval, and Pem. And this theory sticks out because they stuck their necks out. They made a concrete testable prediction, which is always a dangerous thing to do. And that brings us to the quasi-linear experiment, which was a dedicated experiment to test the theory. It's rather unique in plasma physics in the sense it's certainly not a confinement experiment, and neither is it in sort of an emulation of a physical phenomena. It's a theory tester. And then we'll talk about the aftermath and where to. And I think it's best in this that I stop along the way for questions. I have a few places marked out because it's very easy to get lost in the beginning. So that's how we'll handle questions, all right? So wait for the stopping points, but then ask away. So the basics. So, from back in the USSR, there's, the Boltzmann equation. Now, we're going to be interested in systems where the characteristic time scales are fast compared to the collision frequency. So in some sense, the collision operator really is doing nothing except kind of keeping F average close to a Maxwellian on a long time scale. Generally talking about electrons, the ions are stationary. The brackets mean a space and a fast time average. And then you have an average and a fluctuation. And you can write the Vlasov-Poisson system like this, evolution, but Hamiltonian evolution, of course, by Liouville's theorem, and Poisson equation for feedback, and it's incompressible dynamics in phase space. And for those of you who are by now addicted to potential vorticity, just think of the distribution function as potential vorticity. I learned of PV going the other way. When I first read about it, I said, aha, this is just like a conserved phase space density. So the arrow kind of points both ways. If you go to a rigorously collisionless system, as for example in galactic dynamics, okay, so really C is gone, you then the idea of course, a Maxwellian is out the window, and you look for BGK solutions, which are, well, BGK stands for Bernstein, Green, and Kruskal, and they're exact nonlinear solutions of the stationary Vlasov equation. And the problem is there's an infinity of them, and then if you ask what's the most probable one, then you go down the road to the theory of violent relaxation by Lyndon Bell and variations thereof. And we won't go too far into that. Always on some long time scales, collisions operate to maintain proximity to a Maxwellian. Otherwise, the story is collisionless. And I'm not going to write the collision operator after this point. So the excitations of this system are plasma waves which interact with the particles. You might ask about eddies, and we'll come to that, okay? The waves, you just linearize the system, and there's the dispersion relation. That's the dielectric function, equals 0. And of course, what immediately catches your eye is the resonant denominator, right? Which of course reflects the contributions from resonant particles where the velocity equal the phase velocity. And that has a parallel with critical layers in fluids. And so you go along, and the waves are compressible in real space. These are the Bohm-Gross waves. So Bohm is the same Bohm as Bohm diffusion, and the same Bohm I learned in the hullabaloo about the movie last summer, who was the first student of J. Robert Oppenheimer. So, but he ultimately made contributions to many things, but one of them was what we call the warm plasma wave or Bohm-Gross wave. But this wave is damped by collisionless damping due to wave-particle resonance, and that damping is related to the slope of the distribution function at the resonance. And, you know, the two kind of fundamental problems, every field has its beloved problems, are the bump-on tail and the current-driven ion acoustic. And here, by the way, turbulence generally equals wave turbulence with wave-particle interaction. And we'll come to further things later. The bump-on tail is just what it says. Imagine a bump on the tail of the Maxwellian. And of course, the presence of the bump creates a region of positive slope, which is unstable. And this is a basic problem, kind of a textbook problem, but it's illustrative. And actually, as you'll see, you can build a laboratory experiment that realizes it. The current-driven ion acoustic involves two species, electrons and ions, with the electrons carrying the current, thus shifted relative to the ions. And you should see the point here that the name of the game is to get the shift big enough so you get instability out of the electrons, avoiding the ion Landau damping with negative slope. The waves here are ion acoustic waves, and just to ruin your day, they have precious little to do with familiar gas dynamic waves. The speed of sound is set by a combination of the electron and temperature and ion inertia, and they are strongly dispersive. So you don't get familiar shocks when strongly excited. You, in fact, that goes down the road to the collisionless shock, which is another beastie of plasma physics that but we won't get into that. And this is not just a textbook problem. The current-driven ion acoustic is one incarnation of anomalous resistivity, which is one approach to fast reconnection, which, I mean, you could not only have another lecture on that, you could have a program, and I think there have been. So this is stopping point one. Any questions here? Bruce? Yeah, well, velocity. No. I mean, it's everything here in this discussion is assumed to be homogeneous in space. Okay, so think of space as, as periodic and homogeneous, and velocity runs is very simple. No drift waves, no tokamaks today until the very end. Any other questions? Keith? Oh, that is the Debye length, to be precise, the electron Debye length. And the Debye length is simply the thermal velocity divided by the plasma frequency. Yes. Well, depends on K lambda Debye. Right, I'm being sloppy. Think of this over one bracket, okay? Yeah. Yeah, it's so second nature to me. I'm so sloppy in places. Any other questions? All right, so onward and upward. So then coming to the quasi-linear evolution equation, and I'm going to most of the time, put Q over M equal to 1 in the spirit of H bar squared over 2M equal 1. And it's very simple. You write the evolution of the average distribution function, where implicitly F has a function of two time scales, a fast time associated with the wave and a slow time scale associated with the F average evolution. And you simply average over position or the fast time scale, which you can look at as a coarse graining. The original derivation was done by a random phase approximation, which I have to say is not necessary. I think it's clearer to look at it in this way. And in this case, then you take the linear response, and that's what quasi-linear means. You stick it in for delta F, and you get a diffusion looking type equation where D is a function of velocity. And this is a kind of well-known equation I first derived by Velikov, Vedunov, and Sagdeev in '61. And Velikov you'll recognize from the magnetorotational instability. And Sagdeev, I think, needs no discussion. So this kind of where it all started. And if we look at the key properties of this, you notice this D of V now has sort of two distinct characteristics depending on the velocity, right? So they're at resonance, it goes to a delta function, and it is, it suggests something familiar from diffusion, an irreversible process. Off resonance, it's basically proportional to the magnitude of the growth rate, and this is basically reversible. In other words, as the amplitude changes, it changes, and for this reason, it is sometimes called fake diffusion, which I'll leave that, for you to contemplate. The non-resonant diffusion for stationary turbulence, which is the goal of people who try to do modeling, is one of the bugaboos, right? Because the question is, if it's stationary, what do you do for the non-resonant particles? And this, as you can guess, this brings in, the need to go outside quasi-linear theory, which is a part of the problem with all this. It also kind of puts the finger at the dual role of resonant and non-resonant contributions, puts the finger on energetics, which we'll talk more about. And the first derivation was by random phase approximation, but ultimately particle stochasticity is fundamental to resonant diffusion. Now, so this is rather crucial, right? The idea for resonant diffusion can be derived from a Fokker-Planck equation. And of course, that implies a Markov process. So, you know, where's the irreversibility coming from? And the irreversibility comes from chaos or particular particle stochasticity resulting from the overlap of phase space islands, right? The width of the island, which is the size of the trapping width, bigger than the interphase velocity spacing. So that's the first point. Historically, that is not the case. It's interesting. Those gentlemen, I suppose were a bit lucky. In other words, they were working on, if you look at the history, they were working on the subject at the same time as Kolmogorov and Chirikov were doing, you know, the basic work on the KAM theorem and Hamiltonian chaos, and they realized they could expropriate it. It's sort of interesting. The key question as to the validity of the linear response points to a fundamental timescale ordering, and that timescale is the autocorrelation time has to be small compared to a trapping time, a scattering time, or the growth rate. And the trapping, I'll talk more about this, but the autocorrelation time is the self-correlation time of the wave particle, of the pattern that a resonant particle sees. So with hearkening back to Mike Proctor's talk a few weeks ago, there's a little more buried in this than simply intoning short and sudden. It's sort of which part of the spectrum. The bounce time is simply the bounce time for a particle in the trough of the wave, and the descattering rate, the decorrelation rate scales as the 1/3 of a kind of turbulent power of the turbulent diffusivity in velocity space. And that might remind you of something from homogenization and flux expulsion. And as you'll see later, the calculation is done exactly the same way. On the subject of, you know, to say it's important, on the subject of the autocorrelation time, it's really set by the dispersion in the Doppler shifted frequency, which is the dispersion in this thing. And you evaluate V at the resonant particle. So it's the Doppler shifted frequency as seen by a resonant particle. And the message there is, of course, this thing becomes very sensitive to the dispersion relation of the underlying fluctuations. Then the fact that tau AC has to be short compared with the bounce time in the trough is easily understood, right? Will the trough change before the particle runs in and reverses itself, thus strongly deviating from linear orbits, or will it not? If it changes before the wave pattern evolves, then it's on its way. If it bounces, then you have a phase space vortex and you're in the trapping regime. So this should tell you, to put it a little more in the modern lingo, the quasi-linear theory is a low Kubo number theory, okay? And you see that by kind of comparing, you know, linear and nonlinear terms, and this comparison of autocorrelation and trapping time is effectively equivalent to the Kubo number being small and the less than 1. And the Kubo number, of course, is set by this autocorrelation time that I was talking about. And the range, rather than the range in space, is a range in velocity, and it's the trapping width. The other thing that quasi-linear theory assumes is all fluctuations are eigenmodes. This is a biggie. Mode coupling is neglected. right? And of course, that all phase-space density fluctuations are proportional to an electric field fluctuation time of velocity gradient. And you might ask, what of eddies? And this restriction is very similar to what we were discussing with Mike, right? In mean field dynamo theory, all the delta B's are proportional to V tilde times B average. It's much the same road going down. So to put this in a larger, some of the, one DM asked me, well, didn't other people do quasi-linear theory as well as the Russians or something? And there were a few early papers, but really the edifice was built by these two gentlemen. And just to put it in context, if you want to read a modernized version, let me shamelessly advertise a textbook I wrote. But you basically have a story of an external drive making a free energy and instability, and you're interested in the evolution of the mean distribution function, depleting the free energy source and driving gamma to zero. Now, what's not included in this is, of course, wave turbulence and nonlinear wave-particle interaction. Of course, the waves can interact, and you go to the familiar story of wave turbulence, and the signature of that is resonant wave coupling, and I think everybody in the room knows this well. But there's also nonlinear wave-particle interaction, or what we call nonlinear Landau damping, which comes from the beats. So basically, the beats of two waves resonating with the particles, and this is, in a sense, Landau damping kicking the can one order up in perturbation theory. And this is a very important physical effect that we'll talk more about. It's very important in drift wave turbulence. You haven't heard much about it, but maybe you should have. And of course, then you go down to nonlinear interactions, coupling to damped modes, etc. So quasi-linear theory ignores this part of the picture. The kind of theoretical approach that we've talked about, kind of putting this all together, was first laid out in the classic lecture notes from Trieste by Sagdeev and Galeev. I still have my copy from my grad school days, which is all about to just fall apart. We also had some discussions about when is these things valid. So it's interesting maybe to revisit that. I think one can do a little better than the discussions we had. I find it useful to think of what's going on in a space of Chirikov parameter, which is the ratio of the island width to the spacing, and the Kubo number. So Kubo on one axis, Chirikov on the other. Chirikov bigger than 1 means the islands are overlapping and the orbits are chaotic. Kubo less than 1 means diffusion, right? And Kubo larger than 1, who knows? Really, quasi-linear theory and weak turbulence processes are all down in this corner. That's where you find where the theory is rigorously, in any sense, valid. Wave turbulence could be over here. You don't really need particle stochasticity for wave turbulence. Avalanching and maybe directed percolation type phenomena might be up here, those sort of longer range memory. And nonlinear, strongly nonlinear waves and such would be up here. And things that I would describe as eddies or granulations thread the boundary, as do things like isolated islands and something I'll refer to as a simple Vlasov staircase. Let me say one thing, as someone who, in addition to teaching, earns his living largely by dealing with real problems in confinement devices. Most of reality sits in these slots around unity, sorry to say. In other words, that you really often sit at a state where the islands are marginally overlapping and you're not sure if the particles are stochastic or not. And you might be particularly concerned with any sort of residual scattering process that kicks you through the separatrix of the island. And likewise, reality has an embarrassing habit to sit around Kubo number order unity in experiments. So, I mean, it's easy to make these plots, but it's less clear, what they mean in a larger extent. Yes, just hang on. So now we can have, this was a break point. Wait for the breaks, but it's a break. Go ahead. Well, I mean, then it would be, I would say if it's a low Kubo, I think it would be indistinguishable from anything else. What makes it interesting identifiably is that it runs to large Kubo. I mean, the phenomenon could exist, but I would think low Kubo avalanching could probably be well described by garden variety diffusion process, right? That's what low Kubo means. It's the long memory that makes it more of a challenge for the quasi-linear theory. I wouldn't call it a restriction. I would simply say I would not apply, this kind of thing up there. I suggest you have a look at Minjun Choi's recently published paper. He has some interesting analyses of data identifying basically avalanching that clearly exhibits high Kubo number. Okay. So yeah. Well, how did they do it? How did they do it? Yeah, but where they get the spectrum from? That's the point. Of course, the usual thing is you get the spectrum from a weak turbulence theory and you stick it into quasi-linear theory, but you're no longer doing quasi-linear theory then. You're using basically a wave turbulence calculation to get the spectrum and you're calculating the flux from that. That is cheating from the realm of quasi-linear theory. The other question, as I say with that, is I wonder if I'll talk more about mode coupling in quasi-linear theory. The interesting question is the resonant particles. Okay, we'll come to that. But the other question you have to ask is it's perfectly possible to do wave interactions in the regime where you don't have stochastic orbits, at which point then it begs the question of the validity of using quasi-linear theory to compute the flux. And then you also, if you're at it, you have to answer the question of how they handle the non-resonant diffusion. The strict use of quasi-linear theory is basically assuming a spectrum of eigenmodes. But we'll come to mode coupling, don't worry. So energetics, how do the books balance? Well, one way is by balancing, an resonant particle kinetic energy is conserved against wave energy density, and these things I think are familiar. Particle kinetic energy is conserved against electric energy density, and this is just a reshuffling. And if you look at momentum, your resonant particle momentum density is conserved against wave momentum density, which is sort of the small amplitude counterpart of what you guys call the pseudo momentum, right? And all of these things can be, and I think, linked to the theory of pseudo momentum and so forth. So, by the way, got to be careful with this thing. Sorry. If nothing else from this talk, you actually got to see a WMD, right? So you accomplished something from being here. So some comments on energetics. The most natural balance is resonant particle versus wave energy density. Energetics drives really is the driver for a two-component, two-fluid picture. And you can think of it as resonant particles and quasi-particles. So this kind of drives a natural way that we think about these problems. So quasi-linear theory is a system. And this, getting back to the question of how you would calculate something, well, you'd start with a distribution, calculate the waves, upgrade the fields from whatever starting noise, then use those fields to update the distribution function and go around the loop and put gamma equals 0. That is a strict quasi-linear calculation with no mode coupling involved. And all modes here are naturally set by the roots of the dispersion relation. So the outcome, what happens in a real problem? Well, what happens in a real problem is you form a plateau, right? So basically what happens in the bump on tail, as you might guess, the bump tends to fill in. What is interesting is, and that, by the way, is a textbook case of what I might call inhomogeneous mixing, which is the rallying cry of this program to some extent. But more than that happens. You recall the non-resonant diffusion is in play, but that tends to heat the body of the distribution. In other words, if you like, it increases the effective temperature here in proportion to the intensity of the electric field. But this heating is one-sided, right? So because you have to conserve momentum totally, so you're shuffling particles toward lower V here, that means in some sense, you expand the bulk in an asymmetric way. So the message here is that the inhomogeneous mixing locally on the tail drives a global readjustment, right? And that is something we have not heard about. Sorry, I'm not a very high-tech person here. This idea of a global readjustment in response to inhomogeneous mixing is something we haven't heard about very much in all our discussions of layering. If you wanted to actually calculate the level, you could balance basically the integrated spectrum with the change in the kinetic energy density. An equal area rule gives a pretty good rule of thumb, as you might guess. More sophisticated question is, why do you get a plateau? Really, you could have two outcomes. One is the formation of a plateau, and one is the vanishing of the D, right? So if the D were to vanish, right, which says the fluctuations were to decay everywhere, you can show from the sort of a simple calculation that the following must be true. And let me say dr at t equals 0 is infinitesimally small. If D resonant vanishes as T increases, that basically boils down to saying F at T is equal to F at 0. But if the waves are damped, F at T has dF dV negative. Well, of course, F at T equals 0 has dF dV positive, which is a contradiction. So bingo, plateaus form. So that's a simple argument for the formation of the plateau. In higher dimensions, you don't necessarily get a plateau, but usually, and the structure of the plateau can get interesting, like in X and V for drift waves, but we don't really have time for that. Now, the companion piece of this discussion, well, maybe I should stop here for questions before. Any questions at this point? Yeah. Right. More particles are giving energy to the waves than losing to it.
So that piece would be that.
It's a natural thing, but if you write down the quasi-linear equation and ask df dt equals 0, there are two possibilities, right? One is d equals 0 and one is the plateau. And a priori, you can't exclude the other one, right? So the point is, I think it's interesting. The natural thing would be, of course, the plateau, but it's not the only outcome. Right. The other outcome is simply that the system evolves to the point that the fields damp out. Yeah, it's because it's the mean field. It's the coarse grain. It's the coarse grain thing. Just think of the diffusion equation, but remember the D is a function of the intensity. Multiply it by F average, you form a quadratic quantity, and you have two possibilities, the plateau or D goes to 0. All right? So I think it's useful to point out what are the single large waves. So large here, large relative to what is the question, and large would be the bounce frequency or the large compared to the growth rate. So this would be the trapping limit, and this leads us to trapping in a phase space island. And this should start sounding familiar to many of you. You get into the business of differential rotation in the island, coupling to coarse graining, leading to mixing by straining and diffusion, and going down the road toward homogenization. And it is pretty much exactly the same thing carried out in phase space. And the upshot is the formation also of a plateau in the distribution around the resonant velocity, but the width of that plateau is set by the width of the island, ultimately, the square root of q phi over m. Now, that observation, we got to have something about staircases. Isn't there a trivial way to get a staircase in this system? And it seems to me the answer is yes. Simply select a group of resonant waves of large amplitude and arrange somehow that, well, say they're stable, that you initialize them and excite them at an amplitude such that the islands don't overlap, and they will form individual plateaus. And then you will have a sequence of individual plateaus, and you would have a sequence of inhomogeneous mixing regions. And bingo, this then is, I would say, a perfectly legitimate staircase in velocity space, made with nothing up the sleeve. And what's interesting in this is there is no appeal to bistability or the S-curve or any of the other familiar friends. All that's required is a sort of separated resonances with mixing around the resonances. And there is a critical comparison of two quantities, namely the trapping width and the separation in the phase velocity. But beyond that, there's none of our usual friends in the staircase industry. And this is, I think, similar philosophically to a point that Massimo was making when he was here, which I don't think very many people got it, but I thought it was an extremely interesting point that the familiar things that are appealed to in the staircase business are sufficient but not necessary. So I thought I'd make that comment as we went along. All right, so another stopping point. Yeah. Forgotten. It's periodic in real space. Yeah. Well, it depends if you have additional, in the problem as I've discussed it so far, no. But if you control yourself, at the end, we'll come to the B&B model a little bit, which has extrinsic damping, which could be a function of position, and then the answer becomes yes. Okay, but that's along the way. Yeah.
Yeah, yes, that whenever you start with these small amplitude fluctuations, we'll start by having no overlap between the
right.
So
you're always going to pass through the staircase. Yes. Yeah, absolutely.
But since there's instability, they will overlap. So your point is in between this transition.
No, my point is bigger than that. So initialize a bunch of stable waves. Okay, so then there's no instability and they just sit there. Okay, you initialize a bunch of stable waves at different resonant velocities. Just make sure they're not so large in amplitude that they overlap. And bingo, you've got a staircase. And the only thing that will limit that will be the slow decay of the whole thing. I mean, it's a kind of a trivial way to make a staircase. And I find it interesting because I thought Massimo, had a very good point there. It's very relevant to plasma physics where you have resonances and you don't have overlapping resonances. And I noticed that after, we continue on merrily with S curves and bistability in the discussion. So I thought it would be interesting to reinforce that. And arguably, Yannick, just for the fusion consumption, I would say if you've got stiff profiles where you may be not overlapping or marginally overlapping, those ideas become very relevant, right? So now we come to, you might say, what's next? So nonlinear wave particle interactions. So speaking of other distinguished people from the program, you may recall Grisha, and I'd paraphrase his talk by saying, before you declare victory, you should calculate the next order term. So what's the next order term? And if you just continue along in orbit perturbation theory, lowest you get quasi-linear diffusion. Fourth order, you get this goodie. And the thing that should get your attention is this beat wave resonance of the particles and the waves here. This becomes sort of the fourth order goodie. And of course, now it's order e to the fourth, and there's a kind of messy coupling coefficient, but it's straightforward to calculate. By the way, it's tempting to dismiss this. I'll tell you why you shouldn't. I'll tell you why in a second. What it is physically is, of course, the diffusion driven by the beat wave resonances, or driven by kind of the counterpart of nonlinear Landau damping. Okay, the reason you shouldn't dismiss it is, yes, these things are higher order in amplitude, but they become resonant in a part of a distribution which is much more heavily populated with particles than the tail, where normally the waves sit, okay? So in some sense, yes, you lose by a factor of E squared over NT, but you gain a factor of the Gaussian in the distribution function. So this is an interesting kind of thing, and it's a promising channel for dealing with, say, scattering of ions in current-driven ion acoustic and drift ITG. It's certainly of interest to plasma physics, and it illustrates the overlapping, as it were, of quasi-linear ideas and nonlinear wave-particle interaction ideas. And there was with Shane Keating, we did a study of application of this to the flux transport problem. So maybe the next question is, what happens when you have kind of stronger turbulence? So what happens to the responses? And this brings us to resonance broadening theory, the physics of strong wave-particle interaction. And the name of the game here is, you can view solution of the Vlasov equation as integration over linear orbits. Now include a component in the orbit that corresponds to scattering by the random electric field, and consider then a statistical average of that response over a distribution of that scattered quantity. And bingo, you will get a broadening of the wave-particle resonance, and the cognoscenti in the audience will note a very familiar dt cubed, where the only caveat here is the d is a scattering in velocity space. So, and here's the full solution here, and it says the wave-particle decorrelation rate scales as the 1/3 power of k squared times the velocity diffusivity, and this defines a broadened width of the wave-particle resonance, which I'll call delta V, which scales as 1/k tau c. So you now have a picture of what an eddy of resonant particles looks like, right? It would have a lifetime of this tau c, it would have a size of delta V and a spatial size of k. This bit of bookkeeping and accounting, I think, is very similar to corresponding things by Rines and Young and Moffat and Kamkar. And I'll leave it to Keith to comment, but it seemed to me in Moffat and Kamkar, you integrated over ray trajectories in the presence of diffusion. And here you're just effectively integrating over particle trajectories and including a statistical fluctuation, which you then average over a distribution and replace by and characterize in terms of a diffusion. So it becomes a very kind of similar analysis. The tau c is also, and there were a bunch of papers looking at this in great detail, a good fit to the Lyapunov exponent for resonant particle orbits in the Vlasov turbulence. And resonance broadening theory is a crude propagator renormalization. I should say there are many attempts to do something fancier with this. You can write down pages, but making sense out of it is a challenge. For those interested in such things, one kind of exception that I think is interesting is that for resonant particles, the intrinsically non-Markovian character of the renormalization collapses, right? It's interesting. And actually for resonant particles, the Ds, the diffusivities or the renormalizations are rigorously Markovian. It's sort of an interesting twist. So now we come to the heart of things, the challenges. So there are a couple of roads. So I'm going to go down this road talking about phase space eddies. And the physical idea that has been underpinning the challenges to quasi-linear theory are there correlated particles that sort of exist in troughs of waves that Cherenkov emit as a group, right? And kind of boost the growth of the instability. So the question is, will you get enhanced emission from these eddies or chunks in phase space? And will granulations couple to available free energy more effectively than waves? And will this then lead to enhanced growth? And this then drives you to start thinking about, hey, maybe we shouldn't look at waves. Maybe we should look at at these granulations or eddies, and drives one to a formulation in terms of the two-point correlation function, right? And this is similar, again, harkening back to the discussion with Mike, the Pouquet, Frisch, and Leira approach to the dynamo. Basically said, let's not do mean field electrodynamics. Let's look at the spectral evolution, and then look at the evolution in the limit of, say, long wavelength, which in principle can incorporate other bits of physics. And so I'm going to talk a bit about the physics of this. I'm going to talk about one particular subset, which was done by Adam, Laval, and Penn, right? And the reason for that is they made a concrete testable prediction. And then we'll talk about the experiment that tested it, okay? So granulations are basically, the idea is now we consider mode coupling, but mediated by resonant particles. So that process necessarily distorts the distribution, and that distortion is like an eddy or vortex. So there must be something else in the fluctuation in addition to the coherent response. And that something else is a granulation. And if you bring that along, that starts to introduce a dynamical friction effect in the mean field evolution, okay? And the dynamical friction effect then gives a new route to energy transfer. And so there's two parts of the story. One is to look at the evolution of the two-particle evolution, and one is to look at the evolution on the right-hand side, which is effectively the evolution of the mean. So this is how the system couples to the fluctuations couple to the free energy. The two-particle evolution is very simple. It simply just becomes relative diffusion, and the one relevant point is the relative diffusion incorporates the usual plus what I call correlated diffusion. And when you can get all this by a bivariate Fokker-Planck theory, and correlated diffusion incorporates incoherent mode coupling mediated through the resonant particles. And to Guillaume, I would say that is the relevant way to include mode coupling in quasi-linear theory. If you're really going to face the resonant particles, you have to go through that channel. And I think the more interesting thing is the right-hand side, and that gives a dynamical friction. And the plasma people will recognize this as being structurally similar to Bolescu-Lenard theory, where in some sense the dynamical friction now is produced by the granulation and really reflects a kind of Cherenkov emission from the granulation or the eddy, and you can think of it as a wake effect. And that's kind of a very quick discussion. So the implications of this is mode coupling enters the growth dynamics, which is really the critical point here. And interspecies drag can solve the stationarity problem, and this introduces new routes to relaxation and subcritical growth. And there's been a lot of work on this topic. Now, I'm going to talk about one set of work which was done by these gentlemen. And there was a series that started in 1980. And the reason why we pick on them is they made a testable prediction. They stuck their necks out. And you know what happens when you stick your neck out, right? So they solved this equation here, which is what we were talking about. By the way, without the dynamical friction, we'll come back to that. And they found a modest but definite enhancement of the quasi-linear growth for the bump-on-tail problem. And they attribute, and this was in all the right parameter regimes, and they attribute this to the consequence of, this is a quote, the modification is a consequence of wave emission by strongly correlated resonant particles. And it was dubbed clump emission, okay? And this attracted wide attention, and there was a big noise. And this, so where are we? We have a long-standing theory. We have serious theoretical questions culminating in a testable prediction. This was some time ago, but they had simulations back then. The results were all over the place. They were awash. And I venture they'd be awash today too, in anything that subtle. So we have no excuse but to look at an experiment. So yes, in the quaint old spirit of earlier times, right? So we come to the quasi-linear experiment. So what is it? It's the traveling wave tube experiment by Tsunoda, Dovale, and Malmberg. And it's a tube in a magnetic field, a vacuum, of course. And there's a beam of electrons that has a mean speed and a spread. So it emulates the beam in the bump-on-tail. It emulates the bump. And there is a helix wrapping around it. And the helix is basically gives the effect of the non-resonant particles. And it's an extremely clever idea because by using the helix, they're able to control the noise in the experiment very effectively. And it's very, very easy to control noise using the helix. So the question is now that this system is, the beam is the resonant particles in the bump and the helix is the bulk. And what kind of growth do you get, and how does the fluctuation spectrum behave? And here's a picture of a real picture of the experiment. So there's a solenoid, and there are the cathodes, there's the helix, and there's the beam, and there's a dump, and there's a channel for probes and all, and you can analyze velocity and spectra and all. And it's possible to measure and to, it's a sophisticated experiment to measure and control the perturbations introduced. It's possible to control their phases. These guys, since it was earlier times, were quite hung up on the random phase approximation. So one of the things was there was a flexibility in this experiment to randomize the phases and see if it made any difference. And interestingly, mode coupling happened, right? If you look at the power spectrum versus frequency, as the beam evolved, you definitely saw a change in the structure of the spectrum. So mode coupling, generally weak turbulence theory is saying that mode coupling is mediated only by the non-resonant particles. And here is clearly an example where it is being mediated by the resonant particles because it's the only game in town. But the more interesting thing was to look at, in some sense, the average growth. And this is admittedly a lousy picture, but it compares one mode in the smooth spectrum of perturbations, the case of non-repetitive noise, and the case of a single wave with very weak noise. So it should be close to linear, and you have to look very carefully to see all the pieces. And the punchline was there was no deviation of the frequency ensemble average growth from Landau to 10%, right? So it was a ringing endorsement of the quasi-linear theory, or in the quasi-linear worldview. And the message was that mode coupling by resonant particles indeed occurs, so the theory is incomplete, Yet in the bottom line, the growth rate tracks the linear Landau pretty damn well. And the quasi-linear theory works for the growth. So in some sense, that's what happens when you stick your neck out, right? And by the way, the big noise dropped precipitously after that. So the traveling wave tube experiment vindicated the theories of the 60s and demolished the Adam, Lavelle, and Penn. I think much more could have been extracted from this: studies of nonlinear transfer, effect of adjustable dissipation in the slow wave structure, which is, I think, very interesting and should be revisited. And of course, it would be interesting to have it now with better simulations, a coordinated numerical simulation effort. So that I think one of the messages of this talk is it might be time to revisit the TWT or its variant. So the quasi-linear summary, and this is to perturb the naysayers, is at this point, quasi-linear theory is not dead yet. And as they say in Monty Python, and let me talk a little bit about how to look at this. You might ask, what the hell happened after all this nice work, right? And you find quasi-linear theory clearly is deficient, as I think everybody with common sense knows, but yet gets the right answer for the growth. And in Tsunoda, Dovale, and Malberg say, to sum up, we have shown that the quasi-linear description of our experiment is incomplete. The correct nonlinear description is as yet to be found. An important clue may be the existence of statistical or dynamical conservation law governing mode coupling effects, which is an interesting observation, right? In other words, is there something going on that the theory didn't grok? And that's where we enter the picture, and that is momentum conservation. Now, anyone who ever played with the Bolescu-Lenard equation knows for a 1D stable plasma, one species, you get 0 for the evolution. And the reason for that is for like particles, the conservation of momentum and energy in the collisions leave the final state equal to the initial state. So the message of that thing that you teach the kiddies in the basic course, or you should, is that in 1D, one species scattering processes are not effective for granulation, and you have to include another species and look, say, at drag on the ions. Unfortunately, the quasi-linear experiment effectively, we think, simulated a one-species plasma. And the only difference is the system is not stationary, so you had growing waves. So there was no way to exchange momentum with the ions because there were no ions, but you could exchange momentum with the waves. So you go through it. I know everyone wants to get their scrumptious Churchill lunch. I'm not in any hurry, for you know what I think of Churchill lunches. So you can go through the calculation and now deal with a non-stationary state. And interestingly, the relaxation operator, the driver, now is explicitly proportional to the growth rate. And you go through the analysis a little further, and you calculate now the new growth rate. And the interesting thing is the new growth rate is an additive rather than a multiplicative correction. And it's additive in a very small quantity. So it's a small additive correction to a linear growth rate, right? And sort of Adam, Lavelle, and Penn had a number approaching 2 here. We have, our analysis says it's an additive correction of order epsilon. And epsilon is of order, say, the growth rate, the growth rate, over the Landau growth rate over the frequency. So Adam, Lavelle, and Penn is inconsistent with traveling wave tube effects, but this calculation is consistent within the error bars. And the issue was this was mindful of momentum conservation. So quasi-linear theory was seemingly vindicated for the gentle bump on tail single species problem, but maybe we find out that the bump on tail was maybe a little too simple a problem to really get at the physics. And yes, you could explain how to reconcile the experimental results with the quasi-linear growth, but maybe you should look at other, maybe a little juicier problems. So maybe I notice people are starting to diffuse for their scrumptious Churchill lunch. So maybe I should stop here and then I can discuss any of the rest with anyone who's interested. I do have some messages for where this matter should go. Well, we did, but I mean, the only physical source of dynamical friction is with the wave. That's what we did in that paper. Okay, now if you bring the ions, then you have a different problem. That experiment cannot do it. Let me just say, there is, for the plasma people, I can't resist this. This is an important point. You recognize this goodie, right? I hope. Right, that's the sort of the equation for the B&B model, Birkin-Braisman, right? And you know the idea, for those of you who haven't had the pleasure, these guys, there's a very important problem in fusion of the scattering of energetic particles by alphane waves. And these gentlemen made the observation that near resonance, you can map that problem to the 1D Vlasov problem, as we've been talking about. So it's really quite an important observation, right? It's the usual kind of game. You realize you can map one problem to another. But in order to emulate that system, you have to account for some extrinsic damping. That's just, would be in the sense, it would be dissipation in the helix, if you wanted to put it in the lingo of the quasi-linear experiment. So your pal Maxime Lesueur and I, when he was in Korea with us, worked on that. And, you know, we found nonlinear instabilities in that system, okay? And here's the punchline. Delta V is proportional to square root of phi, and you'll note the instability is proportional to the damping rate from the model, and that's an unusual scaling. And the reason I'm mentioning is that the presence of background damping, it opens another channel for energy and momentum exchange. And the simulations really confirm this story. And in fact, I think even more telling is that whether you are linearly stable and go non-linearly unstable, or you're linearly unstable, you end up in the same state characterized by the nonlinear instability. So the quick summary, one thing that I think should be done is to revisit the traveling wave tube with resistive coupling of the helix, resistive coupling of the helix as well as capacitive, and make that adjustable. And then you should be able to realize that system. But if you just repeat the experiment as done, you will come to the same place, because you can't fight the momentum conservation. The other idea that is bandied about is to go down the current-driven ion acoustic road, where there are, by the way, also theories and simulations supporting nonlinear growth. But there, the question is how you're going to do it. It's not, one suggestion is using a negative ion plasma. So you have an impurity with a negative charge playing the role of the electrons, and you have ions, and you don't need as big, you don't have the mass ratio problem, and you can generate a drift, and you can look at what's going on in that.
I ask a super basic question.
Sure.
So, since this is what made you blood boil, I mean, in things like mean field dynamics, quasi-linear field means something.
Right.
It's what Keith calls the plane and the next reflection. Right?
Right.
Where does that fit into all of this? I mean, why? I mean, that means something. Does that fit into this? Why does your blood boil if someone went under mean field electrodynamics? Quasi-linear, have to get rid of that. And off I go.
Well, what makes my blood boil is when they do that. I have no problem with that. What makes my blood boil is when they do that and they say, oh, yes, and we explain, everything in the universe. Right? That's what makes my blood boil. But anyway, finish your question.
Well, no, that really wasn't a question.
Well, I mean, in some sense, if you go back to the beginning.
Okay, let me put it down. That means from what you said, and understand of, let's say, quasi-linear theory in mean field effect.
In mean field, well, I mean, it's a question, as I was hassling Mike about, I think, the message here is that there is more going on than waves, right? That's sort of the message, that there is clearly phase space eddies, or we want to call them clumps, and one can go further with that. And that these things are as efficient, or in some case more efficient, in coupling to the free energy source than the waves are, right? That's the message of this interest in nonlinear growth. That's why people went down that road, right? The idea is saying, what happened if you have phase space eddies? Will this thing give you faster growth than just going through linear wave growth, right? So I would say the counterpart of that in mean field electrodynamics, I would say, would be to go further down. This is what you don't like this, but to go further down the road of Couquet, Frisch, and Layerock, right? Which, seems to me to be better suited, and go further down the road even than they did was in looking at incoherent mode coupling effects, which they basically looked at coherent non-local things, and that may be a more efficient generator. Now, we haven't, I mean, I'm not going to go near that, but we have done that for my beloved drift wave zonal flow problem. Okay, there's a Rameswar Singh and me in 2021 in PPCF. And those effects make a whopping big difference. And they completely change the time evolution of things like the growth of the zonal flow and the transition and some of these pretty pictures you've seen over the years. So my message would be that that might be a good road to go down.
Okay.
Mm-hmm. So what's your question? Yeah. Well, I mean, wave particle resonance, I mean, a critical layer is where a wave resonates with the fluid, basically, and you get Landau damping of the wave into the fluid, and you get they call it a Kelvin's cat's eye instead of an island, but it's pretty much exactly the same thing.
And what's the damping mechanism?
Well, there is Landau damping right there, and there's a nice little discussion of the parallel in Landau and Lifshitz, and at finite amplitude, if you like, you go to the trapping, it's kind of the damping as you get in homogenization. In other words, the interaction of straining with coarse graining.
Ultimately.
Yeah, right, yeah. I mean, you need some kind of diffusive damping.
Okay. That's, thank you.
What?
Are you happy about what?
Yeah.
But I think you're unhappy or not.
Oh. Well, I would think you'd be on board with the philosophy of this. Yeah.
First order.
Right.
In distinct from being healed is broad doesn't become the or but deeper. So in that sense I'm encouraged. I'm not totally settled down. First order.
What? So
It's one.
what is it? Right. But in general, no.
Helpful.
Yeah.
Yeah.
I mean, I think.
No. I think you do that. Yeah.
Yeah, so good. Thank you.
I think I must have put you all to sleep. But
I woke up when I saw E to the minus T2.
yeah, I thought that would appeal to you. Yeah. It's exactly the same analysis in a different, yeah.
Thank
Good.
you very much.